One way to create a uniform electric field is to place two plates close to each other, then give one of them a positive charge and the other an equal negative charge. This will create an electric field between the plates that is directed away from the positively charged plate and towards the negatively charged plate. A positive charge feels a force in the same direction as the electric field, while a negative charge feels a force opposite to the direction of the field. Remember that the electric field between two charged parallel plates is uniform and is always directed toward the negative plate and away from the positive plate. If the size of the two charged plates is a lot bigger than the distance between the plates, then the electric field between the plates will be constant. It's pretty easy to calculate the magnitude of this field. You only need to know the total amount of charge on each plate and the area of each plate. But sometimes, the omega is already given, which is equivalent to charge over area. The distance between the plates doesn't really matter, as long as it is much smaller than the diameter of the plates. Let's look at an example of how to calculate the electric field between two charged parallel plates. If each plate is circular with a radius of 25 centimeters and each has a total charge of 0.16 nanocoulombs, what is the magnitude of the electric field between these plates? First, find the area of the plates. Don't forget that the radius should be in meter. Since the plates are circular, you can find the area of the plates using the radius. Then, use this area to calculate the magnitude of the electric field between the plates. Let's have another example, but more complicated. We can begin by drawing a picture. So, here we have one plate that is positively charged and the other is negatively charged. There is an electric field that exists between the plates. To calculate the magnitude of the electric field between the plates, we can use the following equation. This is also an equation you can use when you have parallel plates. We will simply plug in the delta V, which is our potential difference of 800 volts, and the distance between the plates, which is 6.44 millimeters. Notice that we have to convert that into the standard unit of meters by multiplying it by 10 to the minus 3, and we will plug in known values. We should get approximately 1.24 times 10 raised to 5 volts per meter. That is indeed the correct answer to part A of a question. Now, part B. We're putting an electron between the plates. We should guess correctly that the electron would be pulled to the left because it would be attracted to the positive plate and also repelled by the negative plate. So there is an electric force acting upon the electron, and we can calculate the magnitude of that electric force using the following equation. Notice we're using the absolute value of charge. The particle is an electron. So we're supposed to be using a charge of negative 1.6 times 10 to the negative 19 coulombs, but because it's an absolute value symbol, our answer will come out to be positive, and then the magnitude of the electric field was determined earlier. So when we plug in that in here, and when you crunch that down, you should get an electric force of approximately 1.983 times 10 to the minus 14, and the unit will be newtons because it is a force. Now, the question wanted the direction of the force. Then in our picture, the direction would be left. You could say, or pointing along the negative x-axis. Either one of those would be correct, but the question actually just wants the magnitude. So for now, we can just leave this as the answer to that magnitude of force. Now, in part C, we were told that the electron is located 1.43 mm from the positive plate. We're going to end up moving it over to the negative plate. So we have to figure out this distance. We were told that the total distance between the plate is 6.44 mm. So if we subtract by 6.44 by 1.43, we can easily get the distance from the negative charge to the negative plate. Now, in order to calculate the work required to push this electron to the negative plate, we have to use the following work equation, where we have the absolute value of the force required to push the electron times the distance it travels times the cosine of an angle, that angle between the displacement of the electron and the pushing force. Let's take a closer look at that. We've already determined that an electric force is pushing the electron in this space, and the magnitude of that force was this value, 1.984 times 10 raised to the negative 14. In order to push the electron to the right, we're going to apply our own force of the same magnitude. In other words, we have to apply what we might call an external force, and that has to be equal to 1.984 times 10 to the negative 14 Newton. The reason we have to apply this external force is because we want to push the electron towards the negative plate, and the only way to do that is to apply the external force. Now, since we're pushing it to the right, you'll notice that the angle between the external force and this displacement would be 0 degrees. So when we plug into the equation, we're going to plug in 0 degrees for the theta. So we're now ready to plug in the force. The distance it travels is 5.01 millimeter. We have to make sure to multiply by 10 raised to the negative 3. So get into meters again, and then again the angle is 0. And after you plug and calculate, you should get approximately 9.94 times 10 to the negative 17. And the unit of work is joules. And that is the correct answer in part C.